Extrema on an interval. Made easy. The extreme value theorem. If f is continuous on a closed interval, then f has both a minimum and maximum on the interval. Let's take a look at some graphs. Here is our first graph. F of x is equal to x squared plus 1. We have a closed interval, -1 to 2. The graph is also continuous. The extreme value theorem states that since we have a closed interval and the graph is continuous, we will have both a minimum and a maximum. On this graph, we can see that the maximum, or the highest value, occurs at the point 2, 5. We can also see that the minimum occurs at the point 0, 1. Let's take a look at our next graph. We have the same equation, however, the interval is open. The graph is still continuous. Since the interval is open, the extreme value theorem does not guarantee a minimum and maximum. Taking a look at our graph, we have a minimum at 0, 1. However, we do not have a maximum value since the interval is open. Let's take a look at the third graph. The interval is closed. However, the graph is not continuous. Since the graph is not continuous, the extreme value theorem does not guarantee a minimum and maximum. Taking a look at our graph, we have a maximum at 2, 5 since the interval is closed. However, we do not have a minimum at 0, 1 since the graph is not continuous. Absolute versus relative maximum and minimum. Absolute maximum is the highest point on the graph. Absolute minimum is the lowest point on the graph. Relative maximum occur at hill points. Relative minimum occur at valley points. One thing to note, a point can be both an absolute and relative value. Let's look at our graph. We can see that the absolute minimum occurs at point A since it is the lowest point on the graph. A relative maximum occurs at point B since this is a point on a hill. A relative minimum occurs at point C since this is a point on a valley. At point D, this is an absolute maximum since it is the highest point. And it's also a relative maximum since it is a point on a hill. Let's look at point E. This is neither a maximum or a minimum, and there is no hill or valley on this interval. Let's briefly go over critical numbers. Critical numbers are going to help us find our maximum and minimum values. A critical number is when a function is not differentiable at a point C, or when the derivative at point C is equal to 0. Example number 1. Find the extrema on the closed interval. We are given 3x to the fourth minus 4x to the third. The closed interval is -1 to 2. Our first step is to take the derivative. Taking the derivative, we get f prime of x is equal to 12x cubed minus 12x squared. Step 2 is to find the critical numbers. This is done by setting the equation equal to 0 and solving for our x terms. We can see here we can factor 12x squared from our equation. After factoring, we can see that x is equal to 0 and x is equal to 1. After finding our critical numbers, we want to evaluate f of x at our endpoints from the interval and our critical numbers. This table represents those values. From the table, we can see that our minimum is at f of 1, which is equal to -1. Also, we can see that our maximum value is at f of 2, which is equal to 16. Let's take a look at the graph of our problem. Looking at our graph, we can see our maximum and minimum values. Since we have found the maximum and minimum values, this example is complete.